So thanks for everybody for coming down and giving us a little bit of your ear and your time. I'm going to kind of tee this up at a very high level. Try to use some very practical examples to communicate some of the more complicated topics. And coin just some terminology as we go through this to have a common phrase. Because as we know, this technology, we're still arguing over 3D versus additive manufacturing. Now, alone, all the technical terms that we're going to need to term and define all this new language for how to do this. So one of the challenges right off the bat, that's your first one. We need a language to communicate. So as we work through this, we need to figure out how we do that. Go ahead. So evolution of printing. This is a fairly quick one. I'll just kind of pop through it. So prototypes, it went to functional prototypes as the materials improved. Went into in-use parts. Everybody jumped from this functional prototype that said, hey, we have better materials, we have better functioning machines, I can make some in-use parts. One of the things we jumped over on the way there is the opportunity for tooling. This was an opportunity that we can actually apply the existing technologies without the risks and the challenges. So this all was an evolutionary state. It all kind of evolved over time. But what's happening right now? Go ahead. Right now we're jumping into the revolutionary state. Now we're in this just explosion of opportunity. So there's two new things coming in, hybrid parts and repair and modification. This really embodies the whole cloud there. So if you go to the next one, this revolutionary cloud of things that are going on. So if you kind of look around and see what's happening, we've got tooling emerging in these parts. We've got these hybrid parts. What are those? I'll talk about that a little bit, break that down in a minute. But repair and modification. This is another whole sector that has an entire penetration path. Let's go to the next. So what are the projected growths? Now, I'm not an expert on the market on projected growths and trends. This is all Goldman & Sachs data that I pulled out here. And is Terry around? Terry's been here, so we've got some of Terry's data here. I guess we've got Tim here to represent the team. So we're talking about right now in the almost approaching $1 billion market, right? We're almost into the $1 billion. I've seen other estimates that say we're at the $2.5–2 billion market. So different numbers. People are shaking the tree a little bit differently. I think the differences on services and printers and materials are all kind of coming into that. But the interesting trend is if we're here at $1 billion and 215, how are we going to get to this estimate of $40 billion in 2030, 2035? What does that look like? So the experts are saying that those break out into 6 major categories. And I think the interesting thing to look at this category is if we're going to 40 billion in 20 years, healthcare, industry, and aero kind of break out into 3 fundamentally within rounding error and tolerance error, risk measurement, or prediction. Those are about the same. But auto comes in twice, and consumer goods at 1. So it's an interesting slice, but it's an interesting thing to think about and where this might go. And I think the thing to also note in here that's missing is what about downstream metal repair and mod MRO kind of work, all the things that are going on right now where we're doing our aging aircraft and our aging vehicle refurbishment. What about printed electronics? Where does this show up? I think the consumer would start to show up a lot bigger in printed electronics for that number. So there's some things to sort through as we get down through these estimates and start predicting this industry and start understanding. So what I'd like to do now is kind of talk what I see as the practical breakout, some categories. Tooling, maintenance, repair, MRO we call it, maintenance, repair, and overhaul. In-use parts. And I kind of broke them into some categories that I've seen a lot of people using in the industry. They're breaking these different categories out and talking about them. And I tried to give you some examples of those. Mass customization, hybrid where it's additive and subtractive. It's a hybrid process. We're taking advantage of both traditional machining as well as additive. Hybrid non-similar, hybrid gradient, and then additive only. So let's go ahead. I get into this in more detail. So tooling opportunities. What are we doing there? Well, immediately we can extend a tool's life. So we can take a worn out tool, put material back onto it, and extend the life of that valuable asset. So in the auto industry, this is an area where the auto will take full advantage of this. Those molds are tens, hundreds of thousands of dollars of asset. To put that back into play, put it back in and not have cycle time losses, that's a valuable time. Affordable tooling solutions on cladding. So what if we can take a cheaper material, base material, and put a harder surface on top of that, and that tool lasts a lot longer, but I didn't have to pay for an ink and nail entire tool. I have some options there. I have some games I can play on affordability. Additive-only solutions, unique structures. These are things that we're going to go in and say, we have cooling channels, we have deflection structures, we have molds that we can modularize much cheaper than we could previously with machining. MRO opportunities. This industry of aging aircraft in a time when we're not spending a lot of money on new programs. You can count the number of new programs in aircraft on one hand, and many of the vehicle programs on a couple hands. And so that's a very big change over the last even 100 years of military defense. So we have these assets out there that have to keep fielded. They have to stay in play. How can we take advantage of technology and push those further into life and service the industry longer? So using localized replacements, building the worn materials back up, net machining them back, you meet all the existing qualification parameters for that vehicle. You don't have to get into new qual. So some really important things there. Enhancements to aging air assets. So many of these systems were built way before the new alloys even exist. So to qualify a new alloy as a new part is very, very difficult. But now we can actually go back in and say, we just want to add the new alloy in this wear location. The risk is much lower, the opportunity is much higher, the test and qualification is much less. We can actually get these materials into those programs faster and accelerate them into the market. Go ahead. So mass customization, I think probably everybody in the room has seen a lot of this. Medical, implants, bioprinting, actually embedding sensors into the biomass, into the implants. This is getting really popular, this topic of how we're going to do this and build out the knowledge base to be able to put these systems into play. So really, again, I'll talk about some of the challenges in a minute. Knowledge and the information that's required to get and take advantage and leverage these is the key. Automotive. I wanted to put this one in because I think it's really indicative of some of the outside-the-box thinking. So Local Motors is saying that they want to do customized design, and this can be crowdsourced design in this particular case. They want to do distributed manufacturing, and they want to do derivative styles, personal styles. So if you live in the mountains, you might customize it one way. If you live on the beach, you customize it another way. But this is really where in the mass customization sector, I see that the opportunity comes for really penetrating that market. Today, we're not a volume automotive opportunity, right? Additive manufacturing, we all know the volume challenge is mass production. It's a challenge. But if you could order your own car with your own features, now that gets much more interesting. And if you've got a fulfillment agency as a distributed manufacturing in your neighborhood, you might actually be able to hire your friends to make components of your vehicle, bring that together for you. There's some really interesting strategies that come in the future. So just real quickly, just to kind of baseline some ideas. Subtractive only, you have to take a really large raw stock for this simple part. It doesn't have a lot of metal. You end up with a bunch of chips. Okay? Go next. So the subtractive additive scenario allows you to start with a smaller raw stock, whittle your main core product with a smaller chip set, add your additive unique material to it, and then come back and do your final machining. Most of us admit that today we still need to do some near net processing and go to final machining to get the tolerances and accuracies that we know we need. Another one is metal cladding. So metal cladding is similar. Again, You start with a lower cost base material, and then you add the strength and hardness in locations with another cladded material. Additive manufacturing allows us to do these things. We can add these things in, so we aren't paying the price. It doesn't have to be a raw stock that is completely the entire part being hard stock. So what is a graded material? And I wanted to give just a really, really simple example, and I apologize if it's too simple, but this is just trying to really get everybody to understand. If I had a stiff material A and a flexible material B, and I put a load, give me 112, this would deflect over on a stiffness ratio of the material. If I combine two, and I combine them together, bottom, and I deposited that, and I added another to the top, I push that, and this one being the more flexible, the load is not going to get into this part, and it's going to, most of the deflection come out of the top. So when we talk about graded material load, what we're able to do is transition throughout the part from the stiff material to the flexible material. And now we control a new bend curve, and we can define those curves for what we need that part to perform in. So we actually have the ability to design the behavior of that material. I hope that helps make sense on grading materials. Hybrid materials for dissimilar materials. We're seeing this eruption of this opportunity where I have a metal and I want to put it on a polymer, I want to put it on a biomass. How do I do that? These are very discrepant materials. They behave in different temperature spectrums, and they have to find some way to come together and coexist. Well, these hybrid materials, we're looking for those answers. How do we get more of them? We don't need this palette of 2 or 3. We need a palette of hundreds. So how do we get those to come together? We know once we do that we can use them for a wide variety of electronics. Thermocouples, antennas, electronic items like resistors and capacitors. So these are things we know we can do, but we need more technologies that come together and allow us to do that. So and then the additive only, these are probably the two that I could find in the biggest hype right now about real applications. These are things that are really starting to culminate. So the fuel injector is just a part you couldn't do with any other manufacturing technology today. You have to do it through this to realize what was achieved there. In the functional body parts, these biomasses and integrating sensors coming together. This is a new capability that are really going to change the way we do medicine. It's going to change our quality of life. So what are the challenges? Materials. I've said it several times already. It's, of course, going through this. We have to have more materials available. And I'll blow that one out a little bit further in the next slide. Toolpath, degree of freedom. We have to get beyond this planar thinking. And planar was an excellent starting point. But we have to get into three-dimensional toolpaths. We have to start thinking beyond the plane. So to actually take full advantage of what we can do, we've got to get into the 3D path. Throughput, the current throughput of the machines is accelerating. It's getting better, but it was currently still the limiter on what you can do at any kind of volume. You have to get the throughput up. Got to find ways to expand and accelerate that. Scalability. Today, we have the option to buy another machine. And unfortunately, in some domains, we can't even get the machines we've ordered. So we don't have a scalable solution right now today. Even if we had the market today to identify that additive is perfect for, and we're going to go out and accelerate this, you wanted to put it all out there, you couldn't get the machines fast enough. So how are we going to overcome that challenge? How are we going to get past the scalability issue? Material challenges. I said I wanted to blow that out just a little bit more. So open source materials is going to be critical if we're going to get enough bodies on the problem. If you look at all the materials out there, there's not a wide selection base right now, and there's a lot more materials to go after. So how do we get the resources on that? Open source materials is the only way I know of today to start expanding that opportunity. manufacturing will demand materials without the high margin. So it's going to push that way. As we get into manufacturing, you're going to have your premium materials and your commodity materials. We got to find a way to get to that point. Hybrid material systems, the opportunity for us to get in and really be able to mix these in gradient is when we will really start to push the envelope of real true additive manufacturing only opportunities. Gradient materials, it's just imperative. We need that capability so we can push the envelope. So just to give you a quick overview, in the engineering spectrum, when we go in to try to find a material that we're going to put into an application, these are the kind of charts we're used to getting. These are the options we're used to selecting from. Today, our menu is fairly short, and this is not intended to be an exhaustive list, but our menu is certainly not as long as it needs to be. So finding ways to get into more material integration faster is imperative. That's what I had. So any questions? No? Good.